This is a short introductory lecture on algorithms. Algorithms are really all around us. You can find many examples of algorithms in nature, for example, in the way in which bubbles take shape. However, for simplicity, in this class we shall focus on more discrete algorithms which have to do with machines. There have been many success stories of algorithms. For example, shortest path. Every time you use Google Maps to find the shortest distance between 2 points, say in a city, you're using a clever algorithm which does not go through every possibility, but instead quickly determines the shortest path. Perhaps a less common example is that of pattern matching. Here, the example is that you have some pattern, for example, the string A, B, C, and you want to find it into some very long text, where perhaps you do not require that the letters appear consecutively. You may allow an A here, then some random text, then a B, and then a C here. Such problems occur frequently in text editors or genome applications where you have a very large DNA data and you want to find some patterns, for example, to study evolution or mutation. Again, there are clever algorithms which solve these problems without going through every possibility, and we will see some of them. And these algorithms are critical for large-scale DNA applications. Another example is the fast Fourier transform. This is used heavily in audio-video processing, and in fact, I'm using it right now to record these video lectures. One day I got curious and I posted a question on the CS Theory Stack Exchange asking where you can find examples of textbook algorithms in deployed systems. And I got some very interesting answers, and I encourage you to look it up. Basically, many large pieces of software like the Linux kernel and so on have many algorithms that we shall see in this class in them to solve a variety of problems. So in this class, we're going to look both at general techniques to develop algorithms and also various topics. In terms of general techniques, we shall see divide and conquer, dynamic programming, data structures, amortized analysis, and so on. And in terms of topics, we shall cover things like algorithms for sorting, algorithms for matrices, algorithms for graphs, and polynomials. And we also plan to see hardness. This is the general area of trying to establish that some problem cannot be solved efficiently using a fast algorithm. Okay, we now need to ask ourselves, what is an algorithm? Well, first of all, we talk of an algorithm for a function or a problem. The function or the problem are purely mathematical objects which do not have anything to do with computers or the way in which we compute them. They're simply maps that take an input to an output. Now, this function can be computed or this problem can be solved using an algorithm. Now, the algorithm is a simple step-by-step procedure that can compute a function f or solve the problem f on every input x. And the keyword here is simple. We need to ask ourselves what kind of instructions, steps do we allow from the algorithm? Of course, I could have a single instruction, a single step which just says compute f, but that's not very useful and does not correspond to the way in which our computers operate. So, what operations are we going to consider as simple? Well, first we're going to allow some basic control flow. So instructions like if, for, while, and so on. Then, very important, we are going to allow for direct addressing. That is, I'm going to allow to access the n entry of an array A just given the value n in one time step. Okay? This is a very important assumption. I'm saying that in one time step, I can access any location in the memory. This doesn't quite correspond to the way in which computers operate, because in actual computers, the memory is organized in layers. There is the layer which is closer to the processor, there is the cache, there is the RAM memory, which is usually in the order of gigabytes, and then there is the hard disk, which may be terabytes. You can view the internet as memory, and so on. Okay? There are algorithms which take into account all this complexity. For example, they try to optimize which parts of the memory are moved into the cache to make the algorithms go faster. But for simplicity, we shall just make the assumption that any cell in the memory can be accessed in unit cost. And then we are going to allow for basic arithmetic and logic on variables. So if you have variables x and y, you can do multiplication, addition, things like x and y, and so on. And these operations are simple in practice only if the variables are small. Okay, I'm not really allowed to multiply to very large numbers. In fact, we shall see later that the multiplication of two large numbers is a very interesting problem which is still open and for which many clever algorithms have been developed. But if the variables are small, I can consider them as unit cost. For example, if the variables fit into the size of the register of your processors, for current PCs, this is about 64 bits. And in some cases, we shall get a cleaner analysis if we consider variables simple, meaning that I can operate in a unit cost um, regardless of the size. This allows us to abstract from what's the size of the variables, and as long as I'm careful that things still work when the variables are small, of the size that fits in the computer, I may get a simpler viewpoint of the algorithm. Okay, let's now, before getting to other technical details, let's see a very simple example of an algorithm to fix some notation. Okay. Here is an example. The example is computing the maximum of an array. Okay, so the input here is an array A of numbers from 1 to n. And I'm going to denote this with the notation A square bracket 1 dot n, which means that my entries are indexed from 1 to n. I could have indexed them from 0 to n minus 1, and sometimes that's more convenient, but for now let's just stick to this. and the output is the maximum entry, which I can write as the maximum of the set A1, A2, dot, 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 AN. Okay, it's a very simple operation that you may want to do on some array. And here is an algorithm that solves this. Okay, we shall use a variable max, which I'm going to initialize with the first value of the array. And then I'm going to do a for loop going through the entire array and update the maximum along the way. For the for loop, I'm going to use a C notation. So I'm going to have a variable index I that I'm going to start at 2. This should go all the way to n, so I less than or equal to n, and I can be incremented along the way. Okay, and what I do here is that if max is less than a of I, then I can set max to be equal to a of I. At the end, I can return or output max. That's the end of example. This is a very simple algorithm to compute the maximum of an array. And we shall see soon that this algorithm is pretty fast. In fact, pretty much as fast as it gets. That's it for now, and I will see you next time.